Here we are once again. It is the Physical Science 168 video lecture 9. Good. So where are we? We finally introduced the concept of energy. I'm going to review the steps to get to the energy concept, and then we're going to move along into the grandfather clock of all things. Okay, so today's topics are energy, work, power, for starters, and then we'll take it from there. So we start with force, as we did before, and in particular, weight is a force. Now I have some weights here. I have a scale that reads these things in newtons, and this is going to be roughly 20 newtons. And this would be roughly 40, and this I add another 10 newtons, I'm going to bottom out the scale about as much as it'll measure. Okay, 50 newtons altogether. So weight is a force. So we have the letter F. The units are newtons. And I gave the conversion in the past, so we can always look it up. What's a newton compared to a pound? No big deal. Newton's good. And weight is a force. I weigh somewhere between 800 and 900 newtons, for instance. 800 is a good number for some of my examples. Good, so there's force. Then we have work. This is what we had arrived at, and work is a force times a displacement. So if you move a weight, that takes work. Displace as in the sense of moving something. And of course the displacement has to be in the direction of a force, of the force, okay? That's a detail I talked about before. So work is force times displacement, and we're always interested in the units. So I do the square bracket, and we know the Newton is the force, the meter is the displacement. So the Newton times the meter is the joule. J is the abbreviation, the word is joule. Okay. And so the examples, I'm going to do examples right away. In fact, I'm going to do 3 major examples. The first one is to lift 50 newtons at vertical distance of 1.5 meters, because I'm going to use that example later on. Here's a meter, 1.5 meters is 1.5 of those, and then we would have the work would be equal to 50 newtons times 1.5 meters. That would be 75 joules. Okay, so that's my first example. My second example is the one I did the other day where I do a stair climb. So I'm just going to write stair climb. It was the 5-meter stair climb. It was me, 5 meters. And so the work was 800 times 5 was 4,000 joules. So we have 75 joules for lifting these things here that I just brought to class. A full distance of 1.5 meters. Okay. Lift these up 1.5 meters. That's 75 joules. If I lift myself up the stairs, climb the stairs, that's 4,000 joules. In the last example, I'm going to put right here. So example, love the number of things, right? 1, 2. My third example Actually, let's stick with 2. I'm going to save this example for my next concept. Okay, so we have force, and we have work, and we have these 2 examples of work. So next, and this is where I'll use my 3rd example that I was just thinking of. Potential energy, or next, energy is the capacity to do work. Energy is the capacity to do work. And that's abstract because that's independent of any particular system. What we know about is mechanical energy. This lifting things, it's mechanical energy. So that was mechanical work, my 2 examples. So energy is the capacity to do work. And that's what I want to get at now, because I just did this much work. So I must have had the capacity in me to do that much work. So I had some energy in me. But now we want to take this work that was done in these 2 examples here, example 1 and 2, and then talk about potential energy. Potential energy, that's potential energy, we'll just abbreviate it, PE, is stored work. We'll probably get a more technical definition later on, but right now it's just stored work. Can I store work? In other words, can I do some work and store it and get it back again? And my example for that is going to be the grandfather clock. So our homework is going to involve looking up the grandfather clock. My pictures are only so good, and that's not very, but the grandfather clock, so-called, is the perfect example for what we're doing right now. Grandfather clock. Because how does a grandfather clock run? I'm going to draw my picture here. It's a big wooden case. The dial of the clock is up on top. There are weights in the grandfather clock, and you wind them up with a key till they're up here. So this is point A, and this is point B. And in fact, I'm going to let the distance H be 1.5 meters. So we turn a crank and we wind up the weights 1.5 meters. And as luck would have it, a grandfather clock could use this much weight, okay, which we just said was 50 newtons. Okay, 50 newtons worth of weight would be enough to drive a grandfather clock. So what happens here, there are gears, and I'm not going to draw them. You guys are going to look this up and print out some beautiful grandfather clock examples that I know you'll find. So there are gears, and this is hooked up. There's some cord spooled there. There are a bunch of gears, and they go to the hands of the clock and they turn them. So the weight drops and it turns the hands of the clock for an entire week. Okay. So that's an example of stored work, because if you lift those weights up, you've got your 75 joules of work that you've stored, and it's going to slowly drop down in the course of an entire week, and the clock is going to tell time. Okay. So the grandfather clock work, and I'll say approximately 75 newtons for my example, stored in the elevated weight, which has been elevated by 1.5 meters. So yeah, that's the work. It's been stored, and so when you wind up a grandfather clock, that's actually potential energy. It goes ahead and it drops down So I'm just going to write here the weights. You guys fill this in better than I do. The weights drop down. Gears are turned. So gears turn the hands of the clock. Gears turn the hands of the clock. So there's your example of stored work. How much? 75 joules. How long does it last? It lasts an entire week. Okay. So clock runs for 1 week. These are all very realistic numbers. You don't want to wind that thing more often than once a week. In fact, they're usually made to run for 8 days, and just in case you miss it. Clock runs for 1 week. Okay, now we're missing some interesting stuff on the clock, but so far that's what we have. Potential energy, stored work, grandfather clocks would be our project. Clock runs for 1 week. Okay, let's stick with this. So the next question is, how does the clock keep time? Why doesn't it just run down in 5 minutes as opposed to running down in an entire week? And it's the pendulum in the clock that keeps time. So the pendulum in the clock keeps time. And what I'm going to do is demonstrate the pendulum with a couple of examples here. I have a pendulum that is about 25 centimeters long, and I have one that's a full meter long. Okay, we're measuring from the axis up top here to the middle of the weight. Okay, so let me sketch a pendulum for you. So this thing here is called the Simple Pendulum. And it consists of a string and a mass on the end. And as it goes back and forth, the angle changes, and you want to keep the angle fairly small. L, and I have a weight down here at the bottom. As you can see from my example, I have some metal weights there. Now, I don't even have to have a clock because we're making a video here, and there should be a clock going along with the video. This pendulum has a period of 1 second, the short one does. And I'll even just describe that. When the weight goes across and comes back again, that time equals 1 second. So time of one complete oscillation, that's what we'll call it. Capital T is called the period. The period of oscillation, a complete oscillation, it goes across and comes back again. So like I was saying, we have a clock attached to this video, so this should be 1 second exactly. Back, okay, so 1001. Now if we do it 10 times, then you can actually time this on your video and see if it's really true. So I'm going to start right now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So when I said 10, that should have been 10 seconds from the start. Now this longer period, this longer pendulum has a much slower period, much longer period. And it turns out this is a 2-second period. So a short pendulum has a shorter period, long pendulum has a greater period, but this one is 4 times as long as the little one, and it has exactly twice the period. And to demonstrate that, I'm going to pull them out to the same distance and let go at the same time, and see if you can see the period, the period's the same. Ready, set, go. Okay. See, the little one catches up, and then they leave together again. So for the long pendulum, it's 1 second each way, 2-second period. That's pretty impressive. So there is a law of the pendulum. A law of the pendulum that I'm going to put down next. Now here in my, so the pendulum keeps time, so I have to draw a pendulum now. So there's a pendulum in here, and the question is, how does the pendulum keep time swinging back and forth? In the grandfather clock, there's actually a thing called an escapement, and as the pendulum swings back and forth, it catches the teeth in the gears and it allows them to just shift 1 click at a time, okay? So instead of just winding out all at once, 1 second or 1 little click at a time is how much the gears turn. And these are things I want you guys to look up and get some really nice images. You'll find, you'll even find little moving images online. You can't really incorporate those into your notes, but you can print out some good ones. So let me formulate our homework right now, and then we'll keep going. Yeah, good. So we've got all the numbers right there. So by the way, this pendulum thing, I'm going to erase this now and formulate our homework. This is the pendulum. I'm going to formulate the law of the pendulum, and then I'll formulate the homework. I guess I'll erase over here. Only using one board today. A little more erasing. Okay, law of the pendulum. Law of the simple pendulum. This is in fact the general law of the pendulum. Period of oscillation T is equal to 2 pi times the square root of L divided by G. Now L we already know, that's the length of the pendulum. Length in meters, and G is a number that we're going to get to know a lot better, and its value is 9.8 meters per second squared. 9.8 meters per second squared, that's G. And one thing I want you to do is evaluate this formula and see if it makes sense. So now I'm going to formulate a bunch of homework problems. And hopefully I don't forget any. Okay. So that's the law of the simple pendulum. So homework. Find, by calculating, the period of the pendulum of length L equals 0.25 meters, L equals 1.0 meters. You're going to find them to be very close to 1 and 2, but there will be some decimal points involved as well. On the other hand, I could ask you, that's 1, 2, find the exact length of the 1 second pendulum. Like I said, these are going to be very close, but so find the length exact of the 1 second pendulum. Okay, now how do we do that? I'm actually going to do it for you right now or get started. We have to solve this equation for L. I'm going to name this equation star, and what we do is we square both sides. So now we have t squared is equal to 4 pi squared L divided by G, and now we solve for L. That means L is equal to G t squared over 4 pi squared. Okay. Gt squared over 4 pi squared. And if you plug in t equals 1 second, you've got about 10 divided by whatever 4 pi squared is. Okay. So you have to plug 1 in right here, that's no problem. You've got your 9.8 4 pi squared, and then you'll get a length that's very close to 1/4 of a meter, okay, 0.25 meters. So go ahead and do that and find out what you get. And by the way, once you know this law, you always have a clock at hand. You just need a string. You can set up and count oscillations, and then you know how long something took. Okay. So the law of the pendulum is very useful. So there's 2 things we know about now, actually 3. You cut off a meter, you have a meter stick, a meter length of string, a meter tape, then you have a unit of length for all time. Now you know that if you make a pendulum with a piece of string, you can find your unit of time whenever you need it. And we already know that a liter of water is approximately 10 newtons. So the length, the time, and the force, we already have simple expressions for. Good, so there's the homework. Find the period of the pendulum, find the length, 1 second pendulum, and what I can't control, but I would recommend that you do, is to construct a simple pendulum, hang a string in a mass from somewhere, and test these relations out. Okay, test your own pendulum, and all you need is, like I said, string, tie it off somewhere, you have a weight. Keep the angle, say, under 25 degrees. Keep theta less than equal to 25 degrees, and you'll have a very accurate clock. Good, so that's a good thing to do. Like I said, we already tested this one because there's a clock in the video, and if you let this go back and forth 10 times, or this one as I did, you'll see that it really was very close to 1 second. Okay, continuing with the homework. Now for the grandfather clock. So find images and explanations. For the grandfather clock. In particular, so I'll write that down first, grandfather clock. In particular, the escapement. You want to look up what escapement is and how that functions. I can try to draw a little picture of something you will find if you look. There are different types of an escapement. It's actually pretty sophisticated to make the thing work because the pendulum is swinging back and forth. Okay, there's a thing on top, the escapement, that is catching the gears, catching the teeth in the gears, and it's shaped in such a way that the gears give the pendulum a little kick each time as well. The gears, under the tension of the weight, kick the pendulum each time to keep it going so it doesn't just die down. So that's something I can't draw very well at all. You guys should look it up. But the idea is you've got your pendulum here, it's got a disc, and it has this escapement here, and as this thing rocks back and forth, these teeth here will catch the teeth of the gears that eventually drive the clock. And each time it swings back and forth, it lets the gears ratchet one more time. Good. So that's what I mean, and that's what I'd like you guys to find. Get some good printouts. This grandfather clock is just an amazingly complete machine for everything we're talking about. Work, potential energy, keeping time, and the next concept is also going to be part of the grandfather clock. So that's when we go from force to work to potential energy, and the next concept is power. So let me get my list going here. So there's our homework, by the way. If you get all of these done, you have the little calculation, you want to get some good printouts for the grandfather clock, and I'll keep explaining stuff. First, I'll check the time on our video here. Okay, time flies. Actually, now that we know how the potential energy can turn into work, let's spend a little more time on the work. Potential energy and work. And then we'll finish up with power. So, potential energy and work. So my first example now is the clock. Okay. We have this weight that was, wound up to this height here. It's going to go down, it's going to end up down here. So from A to B, 1.5 meters, and over the course of an entire week, it is going to do 75 joules of work, okay? So it was stored there. In fact, if I just stored it there and shut the clock down, the work would be stored. I'd come back next week and let it run down, okay? Or come back a year later for that matter, let it run down. Okay, so we've got stored work. $75 joules, etc. Now the second example was me and my stair climb. Okay, so I climbed the stairs. I did the work. Can I store it and do other work with it, right? Here we stored the work, and then the stored work ran the clock for us. Here I stored the work, but I'm now at the top of the stairs. What can I do? So there's a question mark. My third example is if I just lift this 10 Newton weight above the tabletop. Okay, 1 meter, 10 newtons, so that's 10 joules. What kind of work can I do with that? I'm going to demonstrate. There's my meter stick, 10 joules of work, okay. So here's what I can do. I can drop it. I can drop it all at once and just imagine that this is a nail, okay? So if I drop a hammer on a nail and that drives the nail into the board, that itself is work, okay? So the 10 joules of work comes down here, drives this into the board. In fact, here, I'll do my little visualization, right? I drop this down here, drive the nail into the board. Okay. So, we'll draw a nail here, and so if we drop the weight onto the nail, it drives the nail into the board against resistance, so that's also work. So drive nail into a board, that too is work. And here's my example now. So 10 joules, so let L equal, I'm just gonna make up a number right here on the spot, 5 centimeters. 5 centimeters equals 0.05 meters. So if that 10 Newton weight can drive the 5 centimeter nail into a board, we have work equals force times length. I'll just write FL, force times length. And I'm going to use these numbers now. That means I have F equals W divided by L. And since we said that was 10 joules divided by 0.05 meters, how many newtons is that? I put it on the homework, but I'm going to do it for you. 10 divided by 0.05, that's like multiplying 10 by 20, okay? So that'll be 200 newtons. Okay, so I'm just going to put that down as the answer. So here, F equals 200 newtons. That's a type of mechanical advantage again. But what happened is it happened almost instantaneously, happened very rapidly. This clock took a week to run down. This thing just took a split second, or a fraction of a second, to convert the 10 joules of work into the 10 joules of work driving the nail. And you can easily imagine 200 newtons. Heck, if you drop this on your feet, it's probably going to be more than 200 newtons, okay? Good. So that's a little bit more about potential energy and work. You can have the work happen really rapidly. I'm sorry, over here really rapidly, or you can have the work happen really slowly. So that brings us up to our concept of power. So potential energy and work. And now we get to power. And then we more or less have the complete set of concepts for this section. So we have work, we have potential energy, and now we have power. So next, power is work divided by time. Okay. So I'm going to use the letter P, W divided by T. And remember, the next thing we always do is ask about the units. This is going to be a surprise to you guys. So the unit of work is the joule, the unit of time is the second, and the joule per second is the watt. And watt is abbreviated with a W. I'm probably always going to write it out because we have too many W's in our life, okay? We have W for work. So joule per second is a watt. And now I'm going to give an example and formulate one more homework problem. Let me check right here. Yeah, always leave enough room in your notes for these homework problems because you can actually work them right into your notes. Okay, if you leave enough space and you didn't get one, you can email me and I'll give the answer on the board and you can put it in your notes as well. Okay, so here's our definition: work per time. The units are the watt. I need a little more room at this board, so I'm going to put this over to the left here. So, power, work per time, the unit is the joule per second, is the watt. Now let's look at our example. The first one I want to do is the stair climb because it has some good numbers. So suppose we do our stair climb and we decided that, come here, we decided that the stair climb was 4,000 joules. Okay. So the power is the work over the time. And suppose I can run up the 5-meter stairs in 5 seconds, which in fact we can do. Okay. Work over time. Example, 4,000 joules, 5 seconds equals 800 watts. Okay. So that's an example of an intense physical exertion, 800 watts. And just for a definition, 746 watts is a horsepower. So that's how it's done, joules per second. So this is a very important example. My next example is going to be homework. Find the power of the grandfather clock that we just defined. Okay. Find power of the grandfather clock. This is going to surprise you. Okay, so me running up the stairs in 5 seconds is 800 watts. What's the power of the grandfather clock when it runs down in 7 days? The power again is the work, and what did we say? That was 75 joules. In fact, it's a completely realistic number for a grandfather clock. Work over time, T is equal to 7 days. Now what you have to do is convert those days into seconds. Okay, so that's 7, and there are 24 hours in a day, 60 minutes in an hour, 60 seconds in a minute. So you have to multiply out this large number, 7 times 24 times 60 times 60. That's the number of seconds in a week. That's what you divide by. You're going to get a very small number. Surprisingly small, because that grandfather clock is bigger than you are, and it's running such a low power. All these things are going to be explained more as the semester goes on, but we're already in pretty deep. Okay, so we have now force, work, potential energy, power in mechanical systems. Okay, we're well on our way, and we have the law of the pendulum, so we're well on our way. I think I'll just say that, yeah, this was a good set here. Let me see if I have anything else to recapitulate. Your homework was these numerical calculations, the pictures of the clock, the escapement in particular. This is just a number here. So yeah, leave plenty of room in your notes, and all this stuff is going to fit together. Okay, the whole progression of ideas is just unfolding. Okay, good. We'll leave it at that. See you guys next time.